Hello, my name is Chun Park. I'm going to talk about some background of this project development and a little bit about the technical aspects. There are 4 people involved in this project, me and Jim Park from Park Seismic, located here in Shelton, Connecticut, and Nils Ryden and Josephine Stockhammer from Norfitech, based in Lund, Sweden. I will talk about each participant a little bit more later again. So this project will be dealing with the hot mix asphalt, HMA pavement, more specifically in terms of evaluating its stiffness and thickness, both of which are very critical properties, not only during the construction, but also during the maintenance stages. And here we see I put this VS, which is a seismic shear wave velocity, as a synonym to stiffness, and I will talk about why in a minute. So this project will be dealing with the measurement of shear wave velocity and thickness of HMA pavement layer. And we're going to use seismic approach. And how does this seismic approach compare to the conventional approaches that have been measuring this stiffness and the thickness of HMA layer? Well, there are pros and cons, but if this works properly, then there will be a lot more pros than cons. For example, most of the conventional methods like coring, density, gravity, they are not measuring direct stiffness properties. Rather, they are measuring indirect properties like density and gravity. And they are basically spot checking methods, and most of them are destructive methods. Whereas this seismic approach will be dealing with the seismic waves, also known as elastic waves, which are responding to elastic properties of materials. So this elasticity is a lot more closer property to stiffness property. And it is a wave approach, which means it can scan on the surface, which becomes completely non-destructive method, and the measurements can become continuous so that we can generate this kind of 2D cross-section or 3D scanning maps. The specific seismic approach that we will be using is called MASW, Multichannel Analysis of Surface Waves, which was introduced almost 20 years ago and has been spread into this geotechnical community very rapidly. It basically adopts multi-channel approach in both acquisition and analysis and generates this kind of shear wave velocity profile of the subsurface and constructs this kind of very common 2D cross-section of shear wave velocity distribution of subsurface. So here it generates a shear wave velocity. Why is it so important is illustrated on the right side here. Whenever we are talking about materials stiffness, there are 3 parameters or 3 moduli. Among them, these first 2 are most commonly used. One is called Young's modulus. The other one is called the shear modulus. And here are defining equations for each modulus. Well, in short, we see there are 3 terms: density, Poisson's ratio, and shear wave velocity. And we see shear wave velocity is included in both equations as a square term, which means it is the most sensitive term. And in reality, the other 2 terms of density and Poisson's ratio, they don't change a lot for different materials, whereas this shear wave velocity change is huge. That's why whenever we can measure shear wave velocity, we can say we can measure stiffness property of materials. There are many MASW projects previously executed at MnDOT during last about 10 years of period, and the most recent one is called SAMS, Compaction Evaluation by MASW Surveys, and results were presented in Park and Richter 2017. It basically dealt with the evaluation of shear wave velocities right below this top pavement layer down to about 1 meter depth. So it dealt with this base and subgrade layers in terms of shear wave velocity evaluation. For this particular project, we will be dealing with this top pavement. Previous SAMS project dealt with measurement by using conventional geophones, which dealt with the frequencies usually lower than 1000 Hz. But for this top pavement evaluation, we will need to deal with much higher frequencies, like a 20 or 30 kilohertz. So we will have to use different approach in data acquisition, and also surface wave phenomena on this pavement layer are slightly different from surface wave phenomena over normal soil sites, so that we have to use slightly different approaches in our data analysis. That's how this project evolved as a separate project after execution of this SAMS project a few years ago. Whenever we are dealing with the surface waves, it is very critical to come up with a very accurate so-called dispersion curves. And here we are looking at theoretical dispersion curves for different shear wave velocities of HMA layer, and for different thicknesses, and for different Poisson's ratios. We can see Poisson's ratios do not make any change in dispersion curves, whereas shear wave velocity change will make the biggest change in dispersion curve at the highest frequency end. In this case, this is 25 kilohertz. Whereas a thickness change will make changes in relatively low frequency range, somewhere between 1 and 10 kilohertz range. So from this theoretical aspect, and also from some realistic perspectives in measurement, we anticipate the accuracy in shear wave velocity measurement will be higher than 98%, and the accuracy in thickness will be higher than 95%. Now let me talk about historical development of this technique, because in order for the seismic technique to become a routine and practical approach that can be used in the field, there are several obstacles we have to overcome. Obviously, because of potential interference with the existing traffic, and also to catch up construction speed. First, early 2000, Ryden et al. Applied MASW approach first to this pavement evaluation in terms of shear wave velocity measurement and its thickness. In this case, that's Ryden at that time used accelerometer to come up with this very nicely developed so-called Lamb wave dispersion curve, and came up with this shear wave velocity and thickness measurement of this concrete pavement. And he had to use this accelerometer, not geophone, because the geophone cannot record this much high frequencies. And this accelerometer was very sensitive device, and it had to be prepared properly. Otherwise, this device cannot record high frequencies. So it took a long time to complete one measurement that provided this shear wave velocity and thickness information at one location. Of course, this was a very monumental achievement at that time, but for this approach to become routine method, still it was far away. It was mainly because of this receiver that took long time for proper preparation. A few years later, Dr. Ryden came up with this non-contact approach that used microphone hanging in the air right above the pavement surface, not accelerometer, and it picked up so-called leaky mode surface waves. Here is the numerical simulation that shows surface waves are propagating along the horizontal direction inside solid material, but we see on the surface of this material there is a small amount of surface wave energy leaking into the air in the form of P waves, which are basically sound waves that can be picked by this microphone. So he came up with this very nicely developed Lamb wave dispersion trend. So everything has become non-contact by this time, which means the measurements can move very quickly. About 10 years later, Dr. Ryden and his student came up with this non-contact and rolling approach. In other words, everything was moving while the measurements were being made. And they used this kind of very compact device which consisted of MEMS microphone. One MEMS microphone is a very tiny device which is smaller than the size of your thumbnail. So this array, which is shorter than 1 meter length, contained 48 MEMS microphones hanging right above the pavement, and came up with this very accurate results. This horizontal axis is the surface distance, so we are looking at shear wave velocity variation from different surface locations on top of the pavement. And different colors indicate shear wave velocity measurements at different temperatures. We see obvious change with the temperature. So everything seems to be ready to become practical approach, but there was one issue still at this time, which was very slow rolling speed. The solenoid impact source was used to generate high frequency surface waves, but this impact source cannot make proper vertical impact while it is moving fast. Therefore, everything had to move very slowly. As Dr. Ryden called it, it was moving as slow as a 100-year-old man's walking speed. But this issue has been solved recently through a brilliant approach that I will show on the last slide. So everything is ready, and we're gonna build this system, and hardware components will have this kind of 2D MEMS microphone array, which will consist of multiple longitudinal MEMS array arranged along the transverse direction so that it can cover about 1 lane with HMA pavement simultaneously. So the total width will be somewhere around 6 feet, and the total length will be probably shorter than 2 feet, and will be towed by regular passenger car or this kind of pickup truck, and everything will be moving at relatively fast speed, somewhere between 10 and 30 miles per hour. And onboard hardware components of A to D conversion and real-time acquisition will collect seismic data in real-time mode and feed into the onboard laptop computer that will be analyzing incoming data in pseudo real-time mode and display the results in 3D format similar to the one displayed here, so that we can see actual variation of shear wave velocities within HMA layer and also its thickness variation as well. So there are 4 proposals. So I'm the principal investigator, and I'll be oversighting the entire project, and I'll be working mostly on the development of software package, and the co-investigator, Dr. Ryden, will be oversighting hardware development, and he'll be working mostly on development of impact source. Another investigator, Dr. Stockhammer, will be taking care of all the electronic components. Her expertise is in the development of state-of-the-art data acquisition system, formerly worked to develop a sonar system to study about the marine dolphins communication. And Dr. Jim Park has been working as operation, training, and administration manager at Park Seismic, and she'll be taking care of all administrative aspects of this project. Here are the summary of work plan and deliverables. This will be a 2-year project, and we will be delivering a system consisting of hardware and software, including 2D MEMS microphone array, plus A to D conversion system, plus a field laptop equipped with software package that includes acquisition, QA/QC, analysis, and display modules. Here is the schedule. This will be a 2-year project, and everything will be done by the end of December 2021, but the final demonstration at MnDOT will be done during May of 2022 to meet the schedule of NRRA meeting. And we will have a monthly Skype meeting to keep track of each other's progress, and we will have an annual joint field test. probably at Lund in Sweden, to calibrate both hardware and software components. Here is the summary of budget. There will be about 135 grand for direct labor cost and about 13 grand for direct expense cost and about 152 grand for subcontractor costs, totaling about 300 grand. Well, from now on, let me talk briefly about some recent developments made at Northitech, and I will make some projection for the next 2 years of our project execution. These are new developments made at Northitech in association with the execution of some other related projects, but I believe they are something that can be easily adopted for our project here. For example, this is a new addition on the back of a regular passenger car made out of modifying regular car bicycle rack so that it holds this MEMS microphone array. And all the electronic components are housed inside. So everything can be attached and detached very easily, and there are no vulnerable and complicated wiring exposed outside here. So at the end of this project, there will be multiple number of this kind of MEMS microphone array arranged along this transverse direction. And this is circuit board of that MEMS microphone array. This is the top portion. And this tiny one element contains 2 microphones at the bottom. And there are 24 elements of this, so that it makes 48 channels in total. So channel 1 starts here all the way down to here for 48th channel. So this is the bottom part of the circuit board, and this one tiny hole represents MEMS microphone, and the spacing between them is less than 1 centimeter. So there are a total of 48 holes at the bottom of this circuit board. And this is a to D conversion box, and all these wires are coming from MEMS microphone array, and all the analog signals coming from that array will go into this box and become digitized, and this onboard computer will control all the data acquisition parameters and will display outputs on this monitor. But recently, Dr. Stockhammer made this small field laptop computer communicate wirelessly with this A to D conversion box. So everything can be controlled from external laptop computer through wireless communication. And this is the one that I was talking about, that very slow rolling speed limited by that conventional impact source. And this one is not conventional impact source. This is a small steel ball hanging from the top of this MEMS microphone array. And it is touching the ground, but when everything starts moving, this ball will be bouncing up and down and making impact. This is a field data example collected by using this approach, and it shows a very nicely developed surface wave event. And it generated this kind of very nicely defined surface wave dispersion trend all the way up to 30 kilohertz. So this will be something that we will be adopting for this project as well after slight modifications, so that we can have a control over impact time and also impact strength. So let me show this approach in motion. So this is that MEMS microphone array, and this is that steel ball. So pay attention to this part, and you will see this one will move up and down, making sound. That's when it is making impact on the pavement surface. And that's it. Thank you very much.